Hi class, welcome back again. Today's lesson, we are going to explain the existence of a magnetic force when a straight current carrying conductor is placed in a uniform magnetic field. And we're going to derive and use the equation. And class, this is Puan Anita Raj teaching for Form 6 Physics Semester 2 on the chapter of magnetic field.
Hi class, on a force on a current carrying conductor. I have a conductor class, area A, length L. This is the length L. This is the area A. This conductor have free electrons. And they are moving with the drift velocity v in this direction. This conductor is placed, or before that, the free electrons are moving in this direction, so therefore there is a current which flows in the opposite direction. Now this conductor is now placed inside a magnetic field. Okay, is placed inside a magnetic field which is uniform, and the strength of the field is B, or we say the magnetic flux density is B. Now what will happen to the current carrying conductor once it's placed inside the magnetic field class? The current carrying conductor will experience a force. Therefore, today's lesson we are going to talk about that force. Today's lesson we are going to talk about what? About that particular force, and we are going to derive and use the equation. We're going to derive and use the equation, and we're going to explain how the force exists. Okay? Alright. Now, in order to find the force experienced by the current carrying conductor, we can look at the first part. Is to find the force by this negatively charged particle, which is this electron. So we are going to look at this electron first. So the force experienced by this negative charged particle can be stated the expression as F equals to negative, either I can put Q or I can put E, B cross product V. Okay? Alright. So this expression of the force is used to detect or to find the direction, the magnitude and the direction of the force. The magnitude of the force of solution for this expression will be F equals to B E V sine theta. But for this example that I've just quoted the example, you will realize that the direction of the magnetic field is into the page, and the direction of the velocity is in this direction. You will not realize that the angle between the B and the V is right angle, which is the 90 degrees. So I substitute theta with 90 degrees and I get F equals to B E V. This is the magnitude, yeah. Now, to determine the direction, I have to use Fleming left hand rule. Okay, now Fleming left hand rule, what is the first thing? Is our left hand. The thumb represents the direction of the force. The first finger represents the direction of the magnetic field, and the second finger represents the direction of the velocity. So in this case, the B is into the page and the V is in this direction. So I get my direction of force is downward. By using a Fleming left hand rule, I get my direction of my force downward. But this is downward. When I use this is downward. And since it's a negative here, so I reverse the direction of the force. Therefore, I will get the direction of the force will be upward. And I'm going to label it as F1. And here also, I'm going to label it as F1 and F1. Okay, so I get the direction of my force upward. So this is the first one. Now, the next concept is to apply something that we have studied in our chapter, which is electric current. We know I is equals to Vena, where V is drift velocity, E is the charge, N is number of free electrons per unit volume, and N is equals to number of free electrons per area times length. Area times length. So therefore, from this equation number 1 and this equation number 2, I can substitute these two equations and form another one. So when I substitute this inside here, I will get I equals to V E N A over A L. And I get I equals to V E N over L. And N is I L over V E. Okay, now the next one is to find total magnetic force. On the current carrying conductor. Now each of these electrons are experiencing a force which is in upward direction F1. So it will be F1, here will be F1, here will be F1, and here will be F1. So total magnetic force experienced, F, will be number of free electrons and times with F1. And N is I L V E. And F1 is either you substitute BEV sine theta or you substitute BEV. Now why do I want to substitute BEV is because I go by this example where the V and the B are right angle to each other. So I'm going to substitute that class. So I'm going to put BEV. And therefore I get F equals to BIL. If I substitute BEV sine theta, then my formula also I can get F equals to BIL sine theta. So I already found the direction, the magnitude of the force. Now the third concept is to understand the force on the current carrying conductor. By looking at this formula, I know the force that acts on the current carrying conductor is related to B, is related to I, and also is related to L. So I can write this in the cross product expression as in two ways. The first way, I can write it as F equals to L B cross product, or I can write it as F I B this way. I can write it in two ways. But which way? What's the difference between these two ways? You see, class, if in this expression the I is considered as a vector. In this expression, the L is considered as a vector. The one that I is considered as a vector is used in the older version books, but this one is used in the newer version book. But I'm going to use this class because I'm already familiar with I as a vector. Okay, so I'm going to use this. And I hope you use that too. Alright, now, so the expression will be F L B with a cross product to the current, I'll get the expression. And this force has a magnitude and direction. Now let's look at the magnitude, which we already proved actually, we already derived actually, where the magnitude will be either F equals to BIL. BIL is based on this example. The general solution will be F equals to BIL sine theta. Now, for this force, to determine the direction is by using Fleming left-hand rule. Okay, now your Fleming, use your left hand. The thumb will represent the direction of the force. The first finger will represent the direction of the magnetic field. And the second finger will represent the direction of the current. So this will be FBI. FBI. So let's use this in this example to determine the direction of the force. Now the current is in this direction. Okay, the current is in this direction. And the B is into the page. So if you realize that, you will notice that my direction of force is upward. So I get my direction of my force upward. Alright. So again I explain to you Fleming left-hand rule. FBI. F, the thumb, represent the direction of the force. F, B, I. Okay. The first finger is the direction of the magnetic field, and the second finger is the direction of the current. So here, class, we already find the force. We know the magnitude of the force, which is F equals to BIL sine theta. And the general expression for the force also we know, which is the magnetic force, which is this. And we know how to determine the direction of the magnetic force that is experienced by the current carrying conductor. Okay, in this I just want to let you all know that this one, this F1, is the concept that you use for a moving charge, which is this. This F is a concept that you use for a current carrying conductor. So you have to use the right concept for the questions that are given in the examples. You have to use the right concept on all those questions that are given. If it's given a moving charge, you have to use this concept. But if it's given on a current carrying conductor, you have to use this concept. So that is all, class. Let me explain again. If the question is about a moving charge, you have to use this concept, which is F equals to QVB. But if it is given a question which is on current carrying conductor, you have to use this concept where F equals to BIL. Thank you, class.
From the lesson just now, we have already learned the formula F equals to BIL sine theta. From this formula, you can actually define B in a current carrying conductor. The magnetic flux density B of a magnetic field is defined as the force on a conductor carrying a current of 1 ampere at right angle to the field per unit length. This definition are used for examples like current carrying conductors.